In this video, we're going to continue working some examples of solving polynomial inequalities. So for example, let's solve 4x squared minus 5x greater than 6. Well, the first thing is to get a 0 over here, so let's move everything to this side. So we have 4x squared minus 5x minus 6 is greater than 0. And now we need to factor this. Well, 4 and 6 gives me 24. 24, 8 and 3. So I believe if I got this right, I should get 4x plus 8, no, 4x minus 3 times 4x plus x plus 2. Did I do that right? Minus 2. Plus 3 and minus 2. There we go. And let's check that. 4x squared, you get 3x minus 8x. That gives me a negative 5x. And then negative 6. Good. Greater than 0. So our key numbers are... This becomes 0 when x equals negative 3/4. This becomes 0 when x equals 2. So those are the only places that the sign can change. Well, let's exploit that now. We have negative 3/4. We have positive 2. And we set up our test intervals, testing each of the individual factors, because that helps us determine the overall sign in an efficient manner. All right, if I plug in, so here I need to pick some values here. A good value here is negative 2, a good value here is 0, and a good value here is 3. Plugging negative 2 into this, and here it would give me a negative 8 plus 3, so a negative value. Plugging into here, I get negative 4, so a negative value. But that tells me that plugging into here would give me a positive value, because it'd be a negative value times a negative value. That's a plus, and that's a minus. Plugging 0 in, I get a positive value. Plugging in here, I get a negative value. Positive, negative gives me a negative. Plugging 3 in gives me 12 plus 3 is a positive value. Plugging 3 into there is a positive value. So positive value. And of course I know that it's 0 here and here. So I'm trying to figure out where this is actually greater than 0. And greater than 0 would be over here. So this interval, negative infinity to negative 3/4. I can't include the endpoint because I don't want it equal to 0, only greater than 0. And then 2 to infinity. All right. I don't need to graph the solution set because it didn't ask me to. And now it's time for you to try working an example. So go ahead and solve 2x squared plus 3x less than 5. On the count of 3, I'll reveal the solution. 1, 2, 3. So here again, we take everything to the other side, we factor, then we go ahead and find our key numbers, use that to make test intervals, test the sign, and then conclude, as we did before. Just to make sure we have the hang of this, let's go ahead and work a much more intense example. So let's go ahead and solve this inequality, and then we'll graph the solution set. Alright, so here again, it's the same procedure. Take everything to the other side. Plus 48 greater than or equal to 0. Here we want to go ahead and try to factor this side. Alright, and then once we have that, we need to figure out a way to factor this, right? Here, let's factor it by grouping. So if we group, we have 2x cubed minus 3x squared plus negative 32x plus 48. Then we need to figure out common factors. Common factor here is x squared, 2x minus 3. Here we can factor out a negative 32. What factors out of 32 and 40? Oh, 16. So minus 16 times 2x plus 3. In other words, we have x squared minus 16 times 2x plus 3 is greater than or equal to 0. And we can still factor this because the difference of squares. We have x plus 4, x minus 4, and 2x plus 3 greater than or equal to 0. And now we can get our test numbers, sorry. The key numbers, not test numbers, not critical numbers. I'll eventually get it right. Key numbers. This would be negative 4, 4, and negative 3 halves. Well, this is just a larger example of what we've been doing. Here we have 3 factors, x plus 4, x minus 4, and 2x plus 3. I'll just write total here, the total sign here. And so, breaking that up, we have this. Our key numbers are negative 4, negative 3 halves. You need to do them in order. Negative 4, negative 3 halves, and 4. Plotting those, we end up with 4 different intervals to test. All right. Well, here we can pick any value we want, so negative 5. Here we can pick any value we want, so we need a value between negative 4 and negative 3 halves, so negative 3 works well, or negative 2. Here, 0 is on that interval, and here, 5 is on that interval. Again, any numbers on those intervals work. Plugging them in, we just want to know whether we get something positive or negative. Here we would get something negative. Here we would get something negative. Here we would get something negative. A negative times a negative times a negative, it gives a negative. By the way, here we know it's equal to 0, 0, and 0. Plugging negative 3 in, we get a positive. We'd get a negative. Negative 3 times 2 is negative 6, so negative, negative, negative is and a positive is a positive. Yeah. 0 plugged in, we get a positive. We get a negative. We get a positive. Positive and positive is positive times a negative, so negative. 5, positive, positive. 10 plus 3 is a positive. So a bunch of positive multiplied together gives me a positive. Now we just need to read off where it's greater than or equal to 0. Well, it's not greater than or equal to 0 there. It starts being equal to 0 there. So that's at negative 4. Then all the way out to negative 3 halves. It equals 0 there, and that's good. Then it's negative, so it's less than 0. We don't want that. Then it starts equaling 0 again at 4. And then it's greater than 0 the rest of the way out to infinity. In other words, if we were to graph the solution set, we would have negative 4, negative 3 halves, and 4. And this would look like plot there, there, plot there, and go out to infinity. So like so. And now it's time for you to try an example. So go ahead and solve this problem, which is similar to the last problem I just worked, and on the count of 3, I'll reveal the solution to you. 1, 2, 3. So again, you bring everything to the other side, factor by grouping, you end up with 3 factors, write them out, find the key numbers, break up the interval, test all the signs, note where it's 0. Here, then you go back and you say, okay, now that I know all the information, we want to know where it's greater than 0. That would be there, and so we write those down and we plot at the end. Now, an interesting thing about this is unusual solution sets in general can occur. What do I mean that can be so unusual? Well, let's look at these examples. So what's unusual about each of these examples? Well, if we go through and we look here, we'll notice that this is always going to be greater than 0 because it's always greater than 4. Because you have something positive, you have something positive. Here, even if you put something negative here, it's always going to be, namely, well, yeah. So basically, this is always going to be positive. So this is always greater than 0. And so our solution set is negative infinity to infinity. It's just any value would work and satisfy that because we all would just want to know where it's greater than 0. This one's interesting, kind of for a flip side. Again, this is always going to be positive because this is really x plus 1 quantity squared. Well, if that's x plus 1 quantity squared, this is always greater than or equal to 0. It's only equal to 0 when x equals -1. And so the only time it can be 0 is just at x equal -1. And that can only be the solution to this. Similarly, down here, because we see this is always greater than 0, this is always greater than 0, and so because of that, we get that the solution set is going to be empty. There's no solutions to this because it's never greater than 0. So here, we notice that this is always, this is really x minus 2 squared greater than 0. But that means that we can't really hit 2. When we hit 2, we equal 0. But otherwise, it'll always be positive as long as we're not equal to -2. Namely, this is kind of weird because essentially, or just x cannot be 2. Or x cannot be 2, sorry, and 2 to infinity. Again, you just kind of go through and you say, well, I can't have it equaling 2 because that would make it 0, but otherwise it's always positive, and so I'm good. And now it's time for you to try and figure out what's unusual about the following solution sets. So I'll go ahead and reveal the answer on the count of 3. 1, 2, 3. So here we see that because this is always positive, because it's a perfect square, it's always positive, which means there's no solutions. This, because it's always positive, and we're wondering where it's less than or equal to 0, means it'll only work when it equals 0, which is when x equals -2. Here we want to know where this is greater than 0. Well, it's always greater than 0, but we can't have it equaling 0. It equals 0 when x is 3, so it's everything but x equal 3. We just kind of go over 3. Finally, here, this thing is always greater than or equal to 0, which means all real numbers will work. For more practice in solving polynomial inequalities, be sure to see page 185 of the textbook and work problems 13 through 40. In our next video, we'll finish off talking about nonlinear inequalities with rational inequalities.